and will get us moving in the right direction. Just kind of a heads up as to where we're at. We're very, very close to the end of Unit 4, which is fantastic because I feel like we're about ready for a test, and I'm ready for a break. I don't know about you all. So in order to do a break, we need to do a test. So today we are going to define elastic and thermal energy as well. We've got some homework to do for tonight. You did not have any homework for last night or for today or whatever you want to call that. We may spend some time with energy bar charts tomorrow. We may just start reviewing. We will take a test. I'm going to say on Wednesday or Thursday. Do you guys have a preference, Wednesday or Thursday?
Let's do it on Thursday. Friday?
Thursday?
Okay. Thursday.
Okay. So let's say Thursday. I think we will probably be in pretty good shape in terms of where we're at on after tomorrow, but we'll kind of get a sense and see where we're at. But we will plan to test on Thursday, okay? Just so that we can have it done prior to winter break. If you know that you've got a bunch of other tests on Thursday, can you not do that so you don't ruin my book? I'd appreciate it. Let me know and we can adjust your test so that you're not stressed out, because I don't want you to have taken 3 other tests and then show up and your brain is so we'll test on Thursday unless you talk to me otherwise individually. So today our plan is to follow up with the Hooke's Law Lab that you worked on Friday. I have those. I have not yet looked at them, but it's going to be a pretty straightforward grade on that. We're going to use that to define spring potential energy. We'll do some practice. We're going to define thermal energy using our experiences with the others, and then we'll do a couple practice problems, and that should get us to the end of the period. Okay? So why don't you pull out your notes? We're going to take some notes, and then we'll kind of intersperse those notes with some practice problems, as I mentioned. So your notes are out. We're actually, I in my head had that we're going to start with springs, but we're actually going to start before springs. We're going to start, cancel. We're going to start with cheeseburgers instead. Yay. So the reason for that is because it's pretty darn straightforward. And the reason for that is that we understand, I hope at this point, doing work in order to get a cheeseburger from the plate to your mouth, or at least to the height of your mouth. Okay? We've talked about this a little bit. We've talked about the fact that if you have a cheeseburger that's sitting on your plate, you lift it up, right? And in doing so, you are doing work. Okay? You are increasing its gravitational potential energy, and then as you take it from it, so if you look at it from the side, if I take the cheeseburger from here to here, am I doing any work? No, because my force is up and my displacement is this way, so no work is being done because they are perpendicular, okay? So again, the only time you're doing work is if you are applying a force parallel to or anti-parallel to the displacement, okay? So what I would like to do here first, where did I put I just had it. Oh, thank you. Thanks for reading my mind and answering my question. I appreciate that. So we're going to do some graphing. And the first graph that I want to do, so we're just going to say graphing force over time. We're going to have 3 examples. So the first example we've got is lifting the cheeseburger. Lifting, let me add a T in there. Lifting. So if we think about that, the work that we're doing is applying a force upwards, okay? And if we assume that we lift it at a constant speed, which seems to make the most sense as opposed to like accelerating it upwards, which seems a little bit more complicated. Tell me about the force that I'm applying to the cheeseburger as I'm lifting the cheeseburger up at a constant speed. How big is that force? How big is the force that I'm applying upwards if I'm lifting it at a constant speed? Maybe not a number, but tell me a way to describe it. Let's draw everybody diagram, shall we? Yes, please. Draw yourself a cheeseburger. All right, there's a cheeseburger. Tell me the force that's acting on the cheeseburger.
Force of the earth.
Force of the earth on the cheeseburger. Which way does that one go, Henry?
Down.
Indeed.
2 for 2.
All right, so you got the force of the earth on the cheeseburger. What else is acting on the cheeseburger? Carbling, right? Carbling is pushing on the cheeseburger. Which way am I pushing? Up. Okay. Now, if I tell you, well, let me ask you instead of tell you, how do those forces compare?
They're equal.
They're opposite in direction. Tell me about their magnitude.
Equal. They have like equal opposite value magnitudes.
Equal opposite value magnitude something. Words coming out of my mouth. All right. So they have equal in magnitude is what Henry is suggesting. If you guys, please. This will go a lot more smoothly if you are quiet when we need to listen. If these forces are equal, or if you think they are, how do you know that they are? What evidence do you have? Go, Jasmine.
There's no acceleration, so the net force would be 0. So if you did that net equation, they'd have to be the same.
Does that seem reasonable? There's no acceleration. We know that is either. So I could that is true if I hold the cheeseburger, okay, or if I lift the cheeseburger, as long as it's not what? Accelerating. As long as it's not accelerating, these two things have to be equal. Quick side question: is this a Newton's third law pair?
No.
Yes.
Yeah.
No,
Yes.
no. That's just too obvious.
No, those are two different forces, not the object on the force.
Because it's not cheeseburger on earth.
What would be the Newton's third law pair for this one?
Cheeseburger on Earth.
Okay, good. Thank you. All right. So to be clear, this is not a Newton's third law pair. If you have two forces acting on one object, then they can't be a third law pair, right?
Right.
Right. Okay, just making sure. All right, so these forces have to be equal. So if I'm talking about my applied force acting on the cheeseburger over a distance, so I'm going to put distance on my x-axis, which is going to feel a little bit funny since I'm lifting it up. So I just want to give you a heads up for that. So this is the distance. So I'm going to put this as the bottom. So I'm going to put that as the table. And then I'm going to lift it up to my mouth. So these are very highly quantified values here. So the table is down here and the mouth is here. And I'm lifting it up. Okay. Now I heard a little bit of rumbling over there before. So the force that I'm going to apply for the most part is going to be equal to the force of gravity, the force of the earth acting on the cheeseburger. Now, if we were going to be very explicit about this and very careful about it, let's think about this. At the very beginning, the cheeseburger is at rest, right? And I need to change the speed of the cheeseburger from 0 to something that's not 0. So just for a moment, tell me about my applied force as I'm getting it started. Has to be a little bit greater than this, right? Are you with me there? Has to be a little bit greater than the force of the earth acting down. Because I got to get it started, so I got to accelerate it just a little bit to get it started. So again, this is like for my calculus friends here, just kind of like a little acknowledgement that there's going to be a little force that's a little bit bigger for just a moment, okay? Just a little distance. And then same kind of deal at the top. And this is one of those things that you've never probably really thought of when you've been lifting food. I mean, you've been doing that since you were, I don't know. I can't remember when your pincer grasp, 6 months old, something like that. You start to learn to pick up those Cheerios, right? And from then on, your body somehow knows to accelerate it just a little bit and then lift it up. And then what happens at the top? Do you just keep pushing with the same force and watching the cheeseburger go up above your face?
No.
No, you don't. Not even when you're a tiny baby. So what do you have to do? The applied force has to do what?
Equal the force of the.
Does it have to be the same as the force of gravity pulling down?
Just be a little less.
Has to be a little tiny bit smaller. Because we got to slow it down so that it doesn't just keep going. No, that would be like a really, really bad movie right there. Okay. like really, really bad. But the non-calculus friends in here and the people that want to keep things simple are going to say, yeah, but friends, this little bleep and this little bleep are going to be pretty much the same. So they're going to even out. But I just want you to acknowledge and be aware that there is a little bit of funny business that goes on here and here in order for us to lift anything that we're lifting up to our mouths or anywhere else. But, just that kind of that whole realization is a pretty big deal. The game is here, friends, that in doing this, the work that's been done, which, oh, by the way, is the change in this case, gravitational potential energy. Gentlemen, I am very, very distracted by what's going on over there. So would you please stop? If you think that you don't need to listen, that's fine. But stop distracting me from teaching. Okay? Thank you. The work is equal to the change in potential energy. Okay? We've known that. That's the Work-Energy Theorem. We've been saying that for a few days. Okay? It happens to be the same as the area under this curve. Okay? This is second semester calculus for you. All right? Doing integrals right now. Boom, we just did it. Okay? We're taking the force, that value, or excuse me, this value, times the displacement, this value, and that gives us the work. Okay? The work is equal to the force times distance, as long as the force is constant, okay, times the distance. The work can be found, or the change in energy can be found as the area under the curve of a force versus distance graph. We said that the force we were applying was the force of gravity, pretty much. The little blip and the little blip here we're going to ignore. So the force is equal to the mass times gravity times the distance up. So sometimes we call that the height, right? The change in height, and that equals the change in potential energy gravitational. So that's really where this comes from, this MGH business that I told you a while ago. Remember I told you that came from somewhere? It comes from right here. Okay? So that's a nice graph of force over time. Yay, go us. Questions so far? All right. We're going to move on to example number 2. Example number 2 comes directly from what you did on Friday. Do you remember what you did on Friday during your lab? No, I don't remember. It's been a whole weekend since then. What did you do? Somebody remind me. What was the goal? What was the game that you were doing on Friday?
The springs and the
Yeah. Springs, displacement, equilibrium, mass. Put those 4 words together and make them happen and everything is good, right? So let's just friendly reminder in case that doesn't sound familiar to you. You had a spring and you had a mass on the spring. And then you added mass, and what happened to the spring?
It went down.
It went down, right? And so you added mass, and then it went do-do-do-do, and then you had another one down here, and it stretched, and do-do-do-do-do, and another one down here. And you made a data table of what versus what? What was your independent variable? Mass. And your dependent variable was distance or displacement from equilibrium. Okay. And then you graphed it, didn't you?
Yep.
Yes, we did, Ms. Carbling. And what kind of graph, my friends? It's been a while since you've done this, and I didn't get your labs back to you to look at it, but let's just see if we can remember. So what did you put on the X and Y axis? I don't remember. Distance and mass. Anybody remember where you put what? Mass was on the X, distance was on the Y. And what kind of graph did you get?
Linear.
Hey, it was a line. Now here's a question for you. If you get a line when you graph mass versus distance, quick question for you, because I'm going to mix this up. This is not traditional for lab work, but for thinking things through and building from it. I'm going to put, I know I'm wild and crazy today. Watch out, it's a Monday. Mass over here and distance over here. What kind of graph am I going to get, friends? Is it going to be a parabola? No, what's it going to be? It's going to be a line. It's going to be a line with slope that's the, oh, hello. Are we really quitting?
What is love?
Is that like the like hold music or what is that? Like, that's just bad? Great. All right.
Is your migraine better?
Are you okay with this? As the mass goes up, the distance from equilibrium goes up. Everybody happy? Okay. Now I'm going to just do something wild and crazy. You ready? Tell me about. We're just going to say no more, okay? Thanks. All right. So as I increase the mass, tell me what happens to the force of gravity pulling this thing down. It gets bigger, right? Now, if this thing's in equilibrium in any one of those places, tell me about the net force acting on it. 0. So what else is acting on that block? Oh, let's draw a free body diagram, shall we? Yes, please. So we got the force of the Earth on the mass. And what else is pulling or pushing on it? Oh. Okay, so let's talk this through. The force of the Earth is equal to mg, right? So as the mass goes up, the force of the Earth goes up. And as the force of the Earth goes up, the force of the spring goes up. We okay with that? So instead of writing mass, I'm going to write force of spring. Are we okay with that? Does that seem reasonable? Okay. Okay. The reason I want to do that is because I want a force versus distance graph. Okay. Kind of like I had on the cheeseburger example. I want a force versus distance graph. Look at that. Now, it's a line. We haven't looked at this. This graph right here, the one that you made on Friday without realizing it, demonstrates something we call Hooke's law. Whoops, there's an E in there. Hooke's law. Okay? So let's talk about what Hooke's law is. It's very straightforward, my friends. Hooke's law says that the force that a spring applies on a mass or on whatever is going to be directly related to the amount that you've stretched it. Does that make sense? The more you stretch a spring, the more it's going to pull. I know, it's wild, right? It's wild, but it's true. Okay, so we're going to say the rule is, let's write it down algebraically, the force of the spring is equal to, so we could say it's proportional to D, but we like equals because equals are more interesting. We got to have some sort of proportionality constant, right? Okay, proportionality constant representing the slope. Anybody want to choose a letter that starts with K? Let's do K, yeah. Times the distance, and instead of D, we often write X. So X is the displacement. Okay. K is known as the spring constant. Okay. And F sub S is the force of the spring, like we just said. There's one other little piece that I've kind of glossed over, but I want to make sure is explicit. Okay? Because directions do matter. Tell me about the direction or the direction of the displacement as I add more mass. Which way does it go?
Yeah.
Down, 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 down. Which way does the spring force go? Up, right? Anytime that you displace something, anytime that you displace like a spring, you pull it this way and the force is going to pull it back the other direction. Are you with me there? Okay. So the last little piece of Hooke's law that's really important is that we need to have a negative sign in there. Okay. That negative sign just means that it's going in the opposite direction. That's all it means. Okay. That the force and the displacement are always in opposite directions. Okay. Hey, quick question about the spring constant before we move on. What are the units of the spring constant? Talk to your neighbors and figure that out real quick. Don't overthink it. Don't make it harder than it needs to be. Look at your units on your equation. What is joules? I appreciate you, Beatrice. What are the units?
Joules.
No. Guesses are not helpful here, friend. Let's do physics and figure it out. What are the units of force? Newtons. You're not stupid. What are the units for X?
Meters.
Meters. If you have meters over here and you just need newtons, then what do you need this to be? Well, that's making it more complicated than it needs to be. Let's not make it hard. Don't make it hard.
Force the earth.
How about let's not guess? Let's figure it out. The question marks you divide by M, right? The question mark has got to be a Newton per meter. That's all it is. Now, if you want to be fancy pants and you want to do kilogram, blah, 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 like you can do that. There's nothing wrong with that. But this is like super simple. I'm just saying. Newtons per meter. That's what they're usually listed in. Newtons per meter. The stiffer the spring, the higher the spring constant. Okay? And that literally just means that it takes more force to displace that spring. Okay? If you think about, so this works for springs, it also works for rubber bands. If you get one of those like big heavy duty rubber bands and you try and stretch it, it takes a lot of force to stretch it just a little ways, right? But if you take one of those little flimsy rubber bands or like a hair tie rubber band, you can stretch it really easily. Are you with me there? Okay? Okay? So that's the whole idea. So we think about that, we think about this, we can figure out now that not only are we applying a force, but we happen to be applying it over a distance. Before we come back to the spring, actually, let's go to that rubber band example. So I'm not going to really do this, but here's a rubber band. You've seen this before. You've done this before. So if I have it like this, it's in equilibrium, right? Okay? If I apply a force in this direction, what am I doing? What am I doing?
Expanding.
I'm expanding it.
Work.
I am doing work, right? I am doing work. Are you with me there? I'm applying a force in this direction,
So because
right?
it's
So over a distance, and I am storing energy in that rubber band. You with me there? I'm storing energy in that spring or in that rubber band. That means I have to be doing work because I'm adding work or I'm adding energy to the system, and that energy happens to be spring potential energy. Okay? If I want to find out how much energy there is, I need to find out how much work I've done. I need to find out the area under the curve. Okay? So let's do it. We're going to find the area under the curve. So what kind of a shape am I going to have this time?
triangle.
Oh, cute. All right, here it comes. So we're going to do this in a couple of different steps. So if I want to find the area under that curve, I need to find this distance there. That's just equal to the force of the spring, right? And this right here is the displacement. But again, we sometimes call that, well, we usually call that X when it comes to a spring. I don't know why they switch between X and D. Somebody I'm sure understands exactly the history of all that. I don't. I just kind of do my deal. So anyway, if we're going to find the work, which is equal to the change in energy, and this energy is not gravitational potential, is it? And it's not kinetic. It's a new flavor of energy today, okay? It's spring potential. Spring or elastic potential. A lot of times we call it elastic potential, but don't call this U sub E because U sub E is electrical potential energy, which is a very different thing, okay? We'll talk about it later, but right now this is what the thing you want to talk about. All right. So how do I find the area of this thing?
1/2 times base times height.
1/2 base times height, right? It's just a triangle. So it's going to be 1/2. Our base is X, and our height is Fs. So that's all well and good, but I want to make it a little bit more interesting than that. A little bit more user-friendly than that because I don't want to have to know what the force is. Not always. Especially not with this energy business. So instead of that, I'm going to use my definition for Fs, which is Kx. Now I'm going to remind you the whole positive and negative directional stuff, we don't really care about that when we're doing this work stuff because I know that I'm doing work, so I'm adding energy. So I really just want the Kx piece here. And I'm just calling this a positive force as my distance gets bigger and bigger. Okay, I have to add more force as my distance gets bigger. So instead of Fs, I'm going to write kx. So now I've got 1/2 x times kx, and that's gross. So let's make it a little prettier. So we're going to say that the change in elastic or spring potential energy is equal to what? 1/2 looks like kx squared. Okay, that's something worthy of putting a box around. All right. How are we doing? Is that making sense? Yay for discovering a new kind of energy today. Good for us. All right. How are we feeling so far? Should we try? Oh, question?
No.
You sure?
Yeah.
Okay. Let's try a problem with this, and then we'll move on to new stuff too. All right. Conservation. Oh, what? This one? From the spring force? Because this force here is defined as kx. K is the spring constant.
Can it be negative?
Should it be negative? No. Because we're not wearing the negative is just saying that the x and the f are in different directions, but all I care about here is the value, not the negative or positive part of it. Is that okay?
Yeah.
All right. Let's try a conservation of energy problem with this. We have done the problem, I think, either in homework or somewhere. We've done the problem of we've got potential energy here, and we've got kinetic energy when it hits the ground. Okay, so we're going to do that problem. We're just going to make it a little more interesting now. Because instead of just hitting the ground, we're going to hit a spring. Okay? So take a look over here. We've got a ball with a mass of 2.6 kilograms starting from rest, falling a vertical distance of 55 centimeters before it strikes a coiled spring, which compresses an amount 15 centimeters. That's kind of weirdly worded. I apologize. It says determine the spring constant. The spring has negligible mass, which means we don't have to do calculus. Yay. So I'm going to give you a minute to look at this problem, to talk about this problem, to think about this in terms of conservation of energy. What kind of energy do I have at these points? See if you can set it up. I'm going to let you work for a minute, and then I'll come back and talk with you too. Question first.
Are we assuming no energy loss?
Yes, we always do. Yep. Until 10 minutes from now, and then we won't. Deal? So enjoy the next 10 minutes, right?
Yeah.
Woo! All right. Give it a shot, my friends.
All right. Here's our spring. So,
Okay.
sorry.
I just we have.
Oh, it's fine.
10.
We're not using Tennessee.
It's 10.
We don't have to touch this.
Yeah, 550 times 2.6.
You see, I'm not sure you're doing that.
Times 10.
See, here's
What?
So the total energy at A has to equal the total energy at C, right? So I'm just throwing all the kinds of energy that might be involved in this situation, which is all the kinds of energy I know about. Gravitational, kinetic, spring potential. What kinds does that have at the beginning?
Potential.
Which kind of potential?
Here. Oh,
Gravity.
gravitation.
Gravitational potential. We got to be a little careful though, right? Does it have kinetic energy?
Not at the top.
Not at the top. Does it have spring potential energy?
No.
Not at the top. So now at the beginning, all I've got is gravitational potential energy. Tell me about at the very bottom. Let's start with the easy one. Does it have kinetic energy at the bottom?
Yeah.
No. Yeah, it should, because the spring energy should have 10.
So kinetic is just talking about the ball. Is the ball moving? When it gets to the very bottom there, nope, because it's going to stop, right? So if you think about this, friends, think about what's going to happen here. So as this ball falls, it's going to gain kinetic energy, right? And it's going to lose gravitational potential energy right here at B, which I've kind of glossed over. But right here at B, what kind of energy does it have?
Spring potential.
Right here,
Kinetic.
it has kinetic.
And
And has the spring yet started to squeeze?
no.
No. So the spring is at equilibrium. So 1/2 kx squared, x is 0. You with me there? If x is 0, that means there's no spring potential energy. No spring potential energy at A, no spring potential energy at B. Okay? Now, you have a choice. And you can do it either way. You can either set H equals 0 here. That's okay. Because then you've got a height, right? And you know where it is. Okay? Or you can set H equals 0 down here. And it does not matter. And the work will work out all the same either way. So there's only kinetic, or maybe there's only kinetic, or there's potential here is gravitational. Down here, when this thing squeezes down, it's taking all of that energy that was kinetic and squeezing this thing down. Are you with me? Okay. So now there's a whole bunch of what kind of energy here?
Spring potential.
Spring potential. Okay. Now, I need somebody to make a decision, and I do not care. Do you want H equals 0 here or H equals 0 here?
First here.
Top one? Yes. Okay. So Courtney's decided that H equals 0, where the book people decided that H equals 0 as well. Okay. So the book people and Courtney agree that H equals 0 here. Now, given that, and I'm glad you said that because it gives us a good opportunity for conversation. Is there gravitational potential energy here?
Yes.
Yes. But what?
It's
negative.
It's negative potential energy. That's okay. Nothing wrong with it. We just have to be aware of it. So we would say then that at the bottom, we've got no kinetic energy, but yes, indeed, we have gravitational potential energy and we have spring potential energy. We doing okay? Do you want me to keep walking you?
Yes.
Okay. Do you want me to let you just play for a minute or no? Just keep walking?
So when after it, okay, so if there was like a D,
Yeah. Where do you want D to be?
and I don't know, after C. So if it shot up, well, right?
Keep talking.
Yeah. So that would be, I mean, what kind of energy would that be? Kinetic then again?
Depends on where you set it. So if C looked like B, then it would be just the same as B. It would be all kinetic. Because we're assuming, Gunnar had asked, are we assuming that there's no energy loss? And the answer is yes. Unless they tell us otherwise, we always assume that there's no energy loss. So that means that if there was a D that looked just like B, but it was going up instead of going down, is that what you're kind of saying?
Yeah, I guess. So
Then there would be no difference because it would just have kinetic, no gravitational potential, no spring potential.
Okay.
Tomorrow's going to be fun.
So as long as it's like touching the
Spring?
and it hasn't like
Pushed it.
affected it yet,
Mhm.
then it's okay.
How are we doing? Are we okay? So let's keep going. So gravitational potential energy is equal to M times G times H. Spring potential energy is equal to 1/2 kx squared. Did you notice that they gave us a mass this time?
Yep.
Do we need the mass?
No.
Let's find out. M times G times, this H is going to be what? At A, how high is it?
H.
55 centimeters. 0.55 meters, good call. Let's do that right now. Oops, not plus. Equals. M times G times, hey, what's the height at C? Negative 15 centimeters, or negative 0.15 meters. I'm going to scooch this over. Plus 1/2. We've got the K. No, we don't have the K. That's what we're looking for. Times, what's the displacement in the kx squared going to be? So x is the displacement from equilibrium. What's that? 0.15.
Wait, sorry, why is it 0.15 now?
Why is it 0.15, Jasmine?
Because if you're H0, so because it compressed the spring, and that's the distance that the force was applied.
From equilibrium.
Yeah, so the spring wants to be here. It wants to be this long. But the ball pushed the spring down 0.15 meters or 15 centimeters. Is that okay? So I think you caught yourself, but I want to make sure that everybody catches this, that it doesn't actually matter if you listen to Courtney or you listen to somebody else, okay? If h equals 0 here or if h equals 0 here, does not matter. That x, that distance that it's compressed, will still be 0.15. Kate, question? Okay.
Actually, now I have another question.
Go.
So, wait, how is that true if h equals 0 is at where that line is? Or at the bottom of y on part C? Then,
Keep talking.
So then, wouldn't that... So, but wouldn't that be 0? Right? Isn't it?
For the h, and h is only for this one. This displacement is just the displacement from equilibrium. How far did it?
Duh.
Yeah.
So it does, I got you.
Yeah. Did you figure out an answer? You're solving for K, right? Jacob got an answer. Oh, that's not a very positive. Oh.
We didn't really use it. You guys end up using
It's negligible.
The value or the result? What are you trying to say?
Just Jacob's answer.
Yes, that's tricksy, isn't it? Yeah. Did you say fine? I need another color. Okay.
Jacob has an answer.
Ellie, I appreciate it a lot. That's awesome.
Scarlett, Jacob has an answer.
Yeah?
That's good.
Do you believe in it more now? Did you get a little boost in confidence?
We deliberated.
Oh, yikes. Do you want to share that answer with me? What'd you get? 1,587? Okay, that's a lot of sig figs. I'm just going to go with that. What are the units? Oh, look at you. So that table has kind of come to an agreement on that. But,
No, I mean Aiden's
positive attitude here, friend. So the other teams, Henry, you need to put that phone away, sweetheart. I don't have to call the. Really? Come on. You know better. You know better. Do you guys agree with that number? Is there any more corroboration for this number?
I'm not done yet.
Nick agrees, but it might be like a warped times. I don't know. Or you guys all rock your physics. I just want to make sure everybody's good too. It's all good. Keenan, do you agree with that answer? Okay. Ellie, do you agree? Yeah?
That's not viable. Wait, actually,
Grace isn't sure, but she thinks she agrees.
I got it.
Sweet.
No,
What's that? Because you did not? Or 5? Me too. Yeah, that's right. All right. I'm going to keep cruising because we've got one more kind of energy we still have to define, and we have 10 minutes. Here we go. We got this. This one will be all right. So, not yesterday, 15 minutes ago, that's what I mean to say. We talked about lifting a cheeseburger. We talked about a spring. Now we're going to do one more kind of energy, This is the one that is related to what Gunnar was asking earlier, and that was, is there loss? You remember that last week we had a conversation about what it means to be a closed system. We said that if it was a closed system, that meant that all of the forces acting were internal forces, right? And that includes the force of friction, okay? So we need to acknowledge that friction is a thing. We need to acknowledge that sometimes, it causes speeds to slow down. So if we get that bowling ball out from, September, and we roll it across the floor, so I give it a push, so I do some work, I apply a force over distance to give it some kinetic energy. Are you with me there? Do you remember this? Rolling. We saw the bowling ball roll, didn't you? Didn't we roll a bowling ball across the floor? Long time ago.
It was a basketball.
Oh, it was a basketball. I'm sorry. Some sort of sphere that rolled across the floor. Okay? In doing that, I applied a force over a distance to get it to speed up, and then I tried to convince you, although you were kind of skeptical of me, that it was going to go on forever, right? I said if there was no friction, but in fact, that kinetic energy eventually would wear off, wouldn't it? By wear off, I don't really mean wear off. I mean be converted into thermal energy. So let's talk about that thermal energy. We know, just as with any other kind of energy, that we can look at it as work. We can look at it as a force acting over a distance. What kind of force brings about thermal energy? It's the force of friction, right? You know, because we've been doing this before, that FF is equal to mu Fn. So as long as you've got a constant normal force, you've got a constant frictional force as something slides across, a space. Okay? So this one's not going to be hard. It's a constant force over a distance. We can find that area under the curve. The work, which in this case is equal to the change in thermal energy. Your book calls that E sub TH. Okay? Sometimes I see it as just H for heat. Okay? Either way is fine. As long as you are marking it in a way that makes sense to you and you're consistent, it's fine. Okay? So the thermal energy is equal to the force, in this case, the force of friction, times the distance. And generally, that's as simple as it is. Okay? There are some problems that you may see where you may have to use your knowledge of the force of friction being mu times Fn. Okay? But in general, it's just going to be the force of friction times the distance. Easy enough? So now, when you're doing a problem, when you're doing a conservation of momentum problem, every time, so it's kind of like when we were doing conservation of, I meant conservation of energy there. When we're doing conservation of momentum, you have to say total momentum at the beginning, total momentum at the end, they have to be equal. Same for energy, but now we've got lots of different kinds of energy. So if you were going to be absolutely thorough when you write out your conservation of energy statement, you would write it out with U sub G and K and U sub S and E sub TH. Every time. I would use the things that are going to be relevant. But if all of them are relevant in a story, then I would use them all. Okay? They're kind of fun when you have all those things in, but we're not going to have that many of them like that. I want to take a look at a problem here before we have to be done today. We've got just a few minutes. We got a couple problems we can work. I'm going to give you this one. This one's from your book. This is not a homework problem, but it's just another one. There were too many fun ones to choose from, so I'm going to do one right now. So a hockey puck is given an initial speed of 5 meters per second. If the coefficient of friction between the puck and the ice is 0.5, the question says, how far does the puck slide before coming to rest? So I could have, if I had a lot more time, have given you this as an opener today, right? Without using conservation of energy, solve this problem. Could you have done it? Yeah, you probably could have. But now I want you to do it with energy. So I want you to think about the kind of energy that it starts with, kind of energy it starts with, kind of energy that the system has at the end, and equate them, okay? We'll let you get started. If you're not sure where to start, then I would draw a picture.
where there's less.
Where there's 10. 10 is a
Yeah,
not 9. That's 0.5. No. Stop.
Did I not do that right?
I just used that like
I got 12 times 9.8 and divide that by.
Oh, yes.
8:25 is almost equal to 5 and 16. So.
It might be on the.
Yeah, no, definitely. It didn't show any work.
Yeah, so weird.
Equal to 24.5 meters. I got 25.4.
It was missed on the last one.
So I can't trust my calculator. I can't trust my calculator. You need a new one. You need to get calculator. I know it's right. I'll just sit right all day. Not really. I can't seem to figure out how to have proper hair ties. I mean, it's like, look at this thing. Look how big that was. I like the size of my grandpa's ears.
What?
Miss Carlin.
Yeah,
When can you cancel out mass?
When there's all
when there's
always-
mass on both sides, when there's mass on every turn.
I think that'll really help your migraine.
Thank
Well,
you.
thank you, Miss Carlin.
Have a great day.
Okay. I heard you guys didn't even turn into English anyway.
No, she's gone. Yeah, we have to read with us up.
Who's this up?
Yes.